Day 2 for circles, we're going to start out with some vocabulary. I'm going to draw a picture over here to the side so that we can kind of get a good look at where each of these occurs in our circle. So if we start here with a chord is a segment with endpoints on the edge of the circle. I'm going to start here with some blue, and our chord is going to be anything that attaches itself to both sides of my circle. A diameter can also be a chord. A secant is a line, segment, or ray that intersects the circle at 2 points. So here we're actually going to extend outside of our circle for a secant. A secant could be something like this here. It intersects in 2 locations. A line, segment, or array that intersects at 2 points. And a tangent is a line that intersects the circle at a single point that we call the point of tangency. So if we take a look here in green for tangent, see if I can get this drawn in here. It's going to hit our circle once and keep going from there. And this little point right here will be what we call our point of tangency. And then our common tangent will be a tangent that is contains 2 different types of circles. So we'll hit those here in just a second. All right, so if we look here at these examples, the center of our circle will be point K. A radius, we have a few different options here. Remember, it starts at the center and extends to the edge. So it could be KI or KJ or KL, either of those, and they are segments, so I'll put the little bar above the top. A chord needs to hit 2 places, and the end points are on the edge of the circle. That's what makes a chord different from a secant. So I'm going to use JL here. There are others, but I'm going to use that one. A diameter has to go through the center of our circle, so JI is our diameter in this case. A line secant will be GI. It intersects the circle twice. A line tangent will be GJ. And a point of tangency will be point J. Remember that our minor arcs are any arcs that are less than 180 degrees. So we could use arc HI if we wanted to do that. And a major arc, if I wrap it around the other direction, remember that for a major arc we use 3 letters. So instead of using HI, maybe we use IJH and work the other way around. A semicircle is going to be an arc that's formed from a diameter, so JI. And our central angle, we have several of them, but I'm just going to use angle, make sure you put that K in the middle. JKL would be an example of a central angle. And a new one that we will actually talk about here in the next few days is an inscribed angle, where our vertex is on the edge of the circle. So one example of an inscribed angle could be angle, let's see, JLK. Notice that I moved that L to be my vertex. All right, how many common tangents do these circles have? In this case, we're just looking for lines that they might share that are tangents. So we've got one here and one here, and then also we would have one straight down the middle. So these 2 circles would have 3. For these 2, we're going to connect them along the edges here and here, but we cannot connect them through the middle. And then for the last set, they share one common tangent over there on the side. So our tangent rules: if a line is tangent to a circle, then it will be perpendicular to the radius. Tangent segments from a common external point are congruent. So think of your party hat. Both sides of our party hat will have the same length, and those two segments, RS and TS, will be congruent to each other. Our question here on this example is ST a tangent segment? So what we know about tangents is that if it is a tangent, it will intersect our radius perpendicularly. So our question here is this a 90-degree angle? And the way that we're going to test that is to test our Pythagorean theorem. So our radius here is 12. I have two legs, 12 squared and 16 squared. And how does that relate to 19 squared? So I'm going to go through and just subtract those. 19 squared minus 12 squared minus 16 squared. And I get a negative 39. So these two are not equal. And ST is not tangent. Given that KJ is tangent to circle L, we want to solve for R. So we're going to use our Pythagorean theorem here, and our right angle will occur here at K. One thing to be very careful of is that this 32 represents the outside edge of that hypotenuse. So the entire hypotenuse is going to be R plus 32. Now when we set this up for our Pythagorean theorem, we're going to have R squared plus 56 squared is equal to, it's going to be really important that you put this in parentheses, R plus 32 squared. Remember that in the case of this piece here, we are going to have to FOIL that. So I'm going to go ahead and leave these two, R squared plus 56 squared. And whenever I FOIL, R times R is R squared. I'm going to have plus 32R plus 32R. So plus 64R plus 32 squared. Rather than multiply those out, I'm just going to leave it. A good thing that happens here is our R squareds will cancel. And I'm going to subtract 32 squared and subtract 32 squared. So whenever I plug that into my calculator, 56 squared minus 32 squared gives us 2,112 is equal to 64R. Divide both sides by 64. And I end up with R being equal to 33. Do not forget to FOIL those pieces in parentheses that are being squared. All right, if we want to solve for X here, I do have my party hat situation. So in the party hat, both of those sides of the hat are going to be congruent to each other. And if I go ahead and set it up, 49 is going to be equal to X squared. When I take the square root of both sides, X could be equal to plus or minus 7. But since we are dealing with a length, we will use, when we square it, it actually ends up as positive anyway. So plus and minus 7 both work. All right, here we have a diagram, and AB is tangent to our circles. What happens here at A and B with our radius, our right angles? And what we're going to do is we're going to move these segments to help us out the most. So it wants us to find the value of X. In this case, I'm going to take the segment AB, and I'm going to drop it down here and split this into a rectangle and a triangle. So if I move my 20 down, now what I have is this long, skinny right triangle. I have a 6 and 8, so that means that this piece is 2 and 20. And now I just need to solve for x with Pythagorean theorem. So 2 squared plus 20 squared is equal to x squared. I end up here with 404 being equal to x squared, and whenever I take the square root of that, this is 4 times 101. So I will bring out a 2 and leave the 101 for my value of x. All right, let's do one more. Let's do number 9. Again, if my right angles are here at A and B, I'm going to move this length of x up. Notice I keep putting those right angle markings in there. That way you can keep track of which one is your hypotenuse. So this section breaks down into 3 and 4, and now we have this triangle that we're dealing with. Here's my right angle. My hypotenuse in this case is 15. Short side is 4, and I'm solving for this, so I've got x squared plus 4 squared is equal to 15 squared. If I do 15 squared minus 4 squared, that gets me 209. And when I take the square root of that, 209 is, let's see, 11 times 19, which are both prime. So we're just going to leave this. It will not simplify. Square root of 209. All right, here we have a bunch of our little party hats in a different situation. They're working our way around a circle. And what ends up happening is that each of these pieces are congruent. So we're going to wrap it around. The 12 will wrap around to this side here. The 13 will wrap around, and the 8. And now we just add them all together. So 26 plus 24 plus 16 gets me a perimeter of 66 centimeters. For the second one, we're going to work with what we can. So my 4 is going to wrap around here. This 5 is going to split into 3 and 2. This 3 wraps around for the other side of its hat. And this 2 then wraps around here, which means of the 4, this piece is also 2, and then this piece is also 2. Don't just make the assumption that that 4 is being split in half. It is, but not because of how it's placed. So add all those up together, and we end up with 22 centimeters. All right, last little set here, we have some chord rules. In a circle or in congruent circles, 2 minor arcs are congruent if and only if their corresponding chords are congruent. So if arc AB and arc CD are congruent, or they are congruent if and only if the segment for the chord AB is equal to the segment for the chord CD. If one chord is perpendicular bisector of the other chord, then it is a diameter. So because SQ is a perpendicular bisector of TR, then I know that SQ is a diameter. Notice that there's not a dot in the middle of that circle. We cannot assume anything to be a diameter unless that dot is there. This little theorem allows us to say it's a diameter because we have a perpendicular bisector. In the same circle or in congruent circles, 2 chords are congruent if and only if they are equidistant from the center. You'll need to have a right angle marking as well as a congruent marking to make sure that you know this. So AB is congruent to CD if and only if the distance FE is equal to GE. And the last one here, if a diameter of a circle is a perpendicular bisector of a chord, let me back up. If the diameter of a circle is perpendicular to the chord, then the diameter bisects the chord and its arc. So if EG is a diameter and EG is perpendicular to DF, then not only is HD congruent to HF, but also those arcs are congruent. So arc FG would be congruent to arc DG. And the last little set here for today, we want to find the length of BD. Because our diameter is perpendicular to our chord, we know that it splits our chord in half. So BF is also going to be 6, and BD will have a length of 12. We want to solve for x. Remember that we can move things around as needed. Let's see, 10x minus 23. If the length from D to both of these chords is the same, then the chords are the same length, and so is the arc. So these two arcs will be the same, and what we do know is that everything around the circle, their measures have to add up to 360. So I'm going to have 2 of our 10x minus 23s plus 106 is equal to 360. Let's see. 20x minus 46 plus 106 is equal to 360. So I'm going to move over those constants. 360 minus 106 plus 46, when I move them over, gives me 20x is equal to 300. And when I divide 300 by 20, I end up with x equal to 15. Find the radius and the measure of arc AB. Remember that the measure of an arc has a degree answer. We're not talking length here. We can put in a radius wherever we would like to. So I'm going to put in a radius from C to B. And remember that if a radius is perpendicular to a chord, then that chord is split in half. So this becomes 12. And we just work our Pythagorean theorem for a 5, 12, 13 right triangle. So my radius is equal to 13 feet. And for the measure of our arc, I'm going to draw this triangle out here to the side just so we can see it a little bit more clearly. Here is AB. Here's point C. And here is that 5. Remember that for the measure of our arc, it is equal to the measure of the central angle. So we need to know this angle here in pink. And we've got 2 right triangles. So what we're going to use is we're going to use some trig to find our theta. So the tangent of our angle theta is going to be equal to the opposite 12 over the adjacent 5. So in your calculator, make sure that you are in degree mode. We're going to do second tangent, 12 divided by 5, and end up with a theta of 67.3 ... And I need 2 of those. So times 2, the measure of arc AB will be equal to, let's just round it to the nearest degree, 135 degrees. All right, 3 more. Find the value of x. Again, we are going to move this radius where it benefits us. So I'm going to move my radius here, and now we have a triangle that is 2 by 3, and we need that length, and then we'll just double it. So 3 squared is equal to 2 squared plus x squared. If I do 9 minus 4, that gets me 5 is equal to x squared. So x is going to be equal to the square root of 5, and if that is half of it, I'm going to double that. So x all the way across would be 2 square root 5. All right, we can again draw in a radius wherever we want. So I'm going to drop it right here, which means that this angle here is 60 degrees. And we can use our 30, 60, 90 rules. So let's see, if 12 is the hypotenuse, then my short leg is 6 and my long leg is 6 square root 3. So the entire way across will be 12 square root 3. And last one, again, we can drop in these radii wherever we would like to. We have a length of 20 and a degree of 86. So if the measure of that arc is 86, then so is its central angle. And if I do 180 minus 86, that gets me 94 degrees for the other part of that. So I'm going to drop in a radius that's going to cut my triangle in half. So I have 10 here. And if I divide 94 by 2, that gets me a 47 degree angle. And if we want to draw this separately, now I have x and 47 degrees and 10. So I'm going to use trig again. I have the side opposite and the hypotenuse, so I'm going to use sine. The sine of my 47 degree angle is equal to the opposite 10 over the hypotenuse x. So to get that calculator ready, we will divide 10 divided by sine 47. And we end up with 13.7 for our value of x.